Hello everyone. Today we are going to learn about equivalence class. Given a set, an equivalence relation R on a set A, okay? Then equivalence class of the element A in that set is defined as this one, box of X. Box of A, we denote it by box. Box of A, X says that X comma A belongs to R. That means X is related with A. So sometimes many writers used to write this X comma A belongs to R as X related with A, okay? Or sometimes they used to write X, this equivalence symbol A also. So what it means here, the equivalence class, say we have a set A, okay? Set A, then some relation is defined inside on the set. So what is equivalence class? Equivalence class are the collection of those elements, okay? Those elements, some X are there, right? Arbitrary elements, X are there. This X is related with A somehow with the relation R, okay? So it will contain some elements here. So let's forward now. So ultimately from the drawing also, figure also, you can say that box of A is a subset of A. Later on you will see that this equivalence classes partition the set A. Now let us take an example, a relation R where A minus B is multiple of 2. Sometimes this one is said to be also A equivalence of B mod of 2. So let us find out the equivalence class of the given relation. This is the relation R. Now the equivalence class of A is denoted by this one. We know this one. Now box of A, equivalence class of the element A, those X where X comma A belongs to R. That means X is related with A. Here what is the R here? R is defined as A minus B is multiple of 2. That means X minus this one X, this one our A, X minus A is multiple of 2. So ultimately if it is a multiple of 2, we can write X minus A is equals to twice K, where K belongs to the integer set. So ultimately X twice K plus 1, this minus 1 minus A goes this side plus A. So ultimately box of A, or you can say the equivalence class of the element A, ultimately it will take this form. Why I am not writing this X? You see X is equals to twice K plus 1. That's why I am writing directly twice K plus A, where K belongs to the integer set. Now let us substitute the value of A is equals to 0. Why? Because this AB R belongs to the set integer set. So I can take any value. You can take minus also. Okay? So 0. So in place of A, I am putting 0. Now it will look like this, twice K, right? Now K belongs to the integer set. K take any value. K is equals to 0 will give 0. If I put K is equals to 1 to 2, K is equals to 2, 2 to the 4. Similarly, it will come out, right? Now if we place K is equals to minus 1, then it will come minus 2 here. If K is equals to minus 2, minus 4, K is equals to minus 3, minus 6. Similarly, it goes on in both sides. Now, let us find the value of equivalence class of element A. Sorry, 1. We have already learned this equivalence class of the element A is equals to twice K plus A, right? So in place of A, I am putting 1, twice K plus 1. Now just put K is equals to 0. What will have? K is equal to 0, 1. This is 1. Now K is equals to minus 1. Then minus 2 plus 1, minus 1. So K is equals to 1. Then 2 into 1, 3. Like this, we just substitute the values of K. Ultimately, you will have this set. Similarly, we can have box of 2, twice K plus 2. Now in place of A, you are putting 2. So ultimately, if you put the value of k 0, 1, 2, -2, -3, whatever, ultimately you will have this set. So it will continue the process like this. Now from above, you see, from above we can conclude that box of 0, that means equivalence class of 0, equivalence class of 2, equivalence class of 4, you see, these are the same element, right? That's why they are equal. Moreover, this is a even integer set, right? Similarly, box of 1, box of 3, right? You see, twice k plus 1, odd integer set. Now look here once. You see, whenever you have this -2 in the equivalence class of the element 2, that means from here we can conclude that box of 2 is equals to -2. Whatever the number of elements are there, and if they are inside of that equivalence class, ultimately they are related with this equivalence class. Moreover, they are equal. That means you can say box of -4 also same. These are the same sets. Okay, and observe these two sets. Okay, these two sets, they don't have any element common. Got it? As they don't have any element common, ultimately we can say that this one intersection this one is equals to 5. Okay, so they don't have any element common. So ultimately from here we can observe that if one element is inside that equivalence class, then ultimately that equivalence class will be the same with that equivalence class of this element. And if there is no element, such element in the equivalence class, then their intersection is equals to 5. Now see here, this is our set, integer set. Okay, now this is our even integer set. Okay, and this is our odd integer. So what you see here, this whole set is partitioned into two. The first two, this one and this one. So from here, thus from above, we can say that the set of even integers and odd integers partition the integer set Z under this given relation R. Or you can say A equals to B mod of 2. This relation is A minus B is a multiple of 2. Okay. So from above, we can conclude that this integer set is partitioned into two. One is even integers and another is odd integers, and they don't have this set and this set, they don't have element common in between them. Okay, thank you.